Okay, so good morning, everyone. Let me thank the organizers for inviting us here. It's always a great pleasure to have breakfast in front of the seashore and to spend some days with colleagues and friends. So thanks a lot. So I will be indeed talking about interactions and associated quantum fluctuations in an interacting Bose gas and the type of correlations being used in the Bose gas. But before, to start with, since I've seen in the program that we are most of us are talking about bosons, and I will as well, I thought I should make the effort to start at least a few slides with fermions. So let me just talk a little bit about fermions and about electrons, actually, if we, to introduce the topic. It will be very brief, just to say that I've spoken about some fermions. So I'm depicting here two, let's say, celebrated examples of strongly correlated electronic materials, so ITC superconductors and frustrated magnets. I will not enter the detail of them, but what I want you to see, which is just like depicted here, is that we have several phase diagrams. So each time you have temperature more or less in the vertical axis, some doping or some pressure on the horizontal axis. And you see that there are many different colors. And this is because you have many different phases of matter. This is the first point, so it's very rich. But not only it's very rich, you also have very interesting and fascinating phases, such as, for instance, the superconducting phase, which are the result of emerging collective phenomena in this type of strongly correlated materials. And one of the questions that is now on the agenda for us is, do we have an understanding, or is there a way to understand from the microscopic point of view, like talking about the single electron, how this type of emerging properties, collective properties, occur on the macroscopic scale? So just to show and to illustrate why it is strongly correlated, I would like to take two examples related to that. Let me start with this experiment. So this is a cold atom experiment, but done with fermions. It has nothing to do with the complicated structures I've just shown before, but I think it nicely illustrates the subtle interplay you have in this type of strongly correlated materials. So let's take here the first picture. What you have are a two-leg system. So with, let's say, sides. The two colors, blue and red, depict the two spins of a fermion, so let's say spin up and spin down. And here, when you have no color, it's because you have a hole. The particularity of this system is that charged particles can move horizontally, but not vertically. But you have magnetic interaction vertically, which favors antiferromagnetism. So therefore, this is the reason why you have always the alternance of blue-red, in order to minimize the corresponding magnetic energy. So if you start with this situation, with two holes, and then you start moving one hole, what happens is that, the red and blue spins have moved, and of course, now you have two blue in front of each other, which is not the best in terms of magnetic energy. And as a result, once you have moved the first hole, in order to minimize and to get back to the magnetic texture underneath, the second hole will move along. And so you will recover just like the same type of texture. And the one thing I want to stress is that in order to understand this, you need at least to consider three objects, two spins and one hole. And if you look in terms of let's say frustration, it also happens, frustration is the case where you start putting spins, like spin down, spin up, and then you wonder which one here you want to put, again, to minimize magnetic energy. And here as well, this type of question occur when you need to account at least with more than two objects. And the point of this strongly correlated material is exactly that. But if you want to look at these systems and try to describe them with perturbative theories, like Landau-Fermi or BCS or other type of, let's say, free quasi-particle theories, you will not manage to do so. And the reason is because in this type of free quasi-particles, you can only account for, let's say, correlations between two objects, mainly, which is not encaptured in these systems. So one need, in order to enter the strongly correlated system, or what I will refer to as strongly correlated, to go to theories which are essentially non-Gaussian. And I will try to illustrate that during this talk. And will not talk about fermions, as I told you, but there are other systems when one can study strongly correlated systems, like electron photons, for instance, that you may have heard about yesterday, and strongly interacting bosons that I would like to address today. And the question is rather simple, is you take a gas of bosons, and now you put some interactions, and you wonder what type of quantum fluctuations are generated, and what type of correlations are associated to these quantum fluctuations. So I'm an experimentalist. How to do that in the experiment when you need to pick up one platform, when you can do that. And what you would like is to have, let's say, of course, quantum effects. I'm talking about quantum fluctuations. So let's say a low temperature, no thermal effect, or minimizing them. You would like to be able to tune interactions, because what you would like to be is to go in a regime where the system is not strongly correlated, measure what happened, and then go to the strongly correlated one and look what has changed. And because I said that I wanted to be able to probe the microscopic correlations, well, I need a probe. And these three things, cold atom, offer them. So I think the assistance is not all cold atoms, so there's just a few slides. Brief reminder about ultra-cold atoms. So we are working with very dilute gases. And as Isabelle mentioned, what we first do in order to go in the regime where quantum effects are prominent, we start by laser cooling them, and then we do evaporative cooling that brings us in the nano-K range. And in this nano-K range, then in the case of bosons, you have this phenomena of Bose-Einstein condensation that occurs, right? And so just to remind you, a Bose-Einstein condensate is the macroscopic application of the lowest energy state in the single particle level. Okay, so we have this Bose-Einstein condensate, and we can even actually produce Bose-Einstein condensates which are essentially non-interacting ones. So now we start from all these bosons in the BEC, and we want to change interaction. So cold atom allows you to do that, and the most, let's say, well-known approach is this so-called Feshbach resonances. So I will not describe them, but just to tell you briefly what happened is that the interaction potential in the ultra-cold sector, you can write it like that as a contact interaction, parameterized by this A, which is the scattering length. And this actually scattering length, you can control it by playing with different energy levels. So during the, let's say, the scattering processes, and you can play with, so atoms are initially in this blue open channel, and you can play with a so-called closed channel, which has a bound state, and you can, if you can tune the distance of this bound state to this open channel, then you will be able to change this value A. And what is often done in experiment is that you can change this value here with a magnetic field, and as a result, the scattering length can vary, and vary very strongly, can become negative, positive, so you have a very good knob. However, for the physics I want to deal with today, it's not very well suited for the following reason. So that if you take a Bose gas and you increase interaction, you go close to the resonance, so which is called the unitary regime, you have two things. So you have a very interesting new physics that kicks in, which is a free body physics, like Efimov-like, which is very interesting per se. But you also suffer large free body losses. And so this means that if you want to study what happens at equilibrium, you will have very hard time because of these losses. And to illustrate that, what I've plotted here is a result from the Cambridge group, where they play with potassium 39. And here, vertically, what you have is the fraction of atoms in the BEC, which is plotted as a function of interaction. You see this A value here, the scattering rate. So you have different experimental data, and what I want to tell you is that this brown data here actually corresponds to 35% of atom losses in the experiment. And you see that they correspond to changing the condensate fraction by only like 10–15%. So this is not a good knob to change interaction. But we have an alternative, and the alternative is optical lattice. So an optical lattice is a standing wave. You shine two laser beams. They create an optical standing wave, and if you are in the good condition, this standing wave creates an optical potential, conservative optical potential essentially, which is seen by the atoms. Well, just a few numbers. And the good thing about optical lattices is that you can basically control depth, geometry, dimensionality. I mean, Isabelle mentioned that you can create 1D Bose gases with these optical lattices. And I'll just put some examples here, which is a very broad, has very broad applications. And many groups are using these optical lattices. So how can we tune interaction with these optical lattices? Well, yes. So an optical lattice is a periodic crystal of light, and so it's actually very much used to mimic Hugbart Hamiltonians, which were initially introduced in the case of electrons moving in the periodic potential created by ions. And in the case of atoms, and particularly in the case of bosons, which I put in this optical lattice, you have essentially two energy scales to describe the system. You have the tunneling, let's say, of one atom from one side of the lattice to the next, which is the tunneling amplitude J. And this is associated to a kinetic term in this Bose-Hugbart Hamiltonian. And if you have two atoms on the same side, then you have to pay the penalty associated to interactions, and which is as an amplitude U here. And so in all this talk, I will consider repulsive interactions. So you have this Bose-Hugbart Hamiltonian. And you see that if now I change the amplitude of this optical lattice, the depth here will change its stiffness, and I will both change the probability of tunneling and also change the on-site interaction, because I am essentially changing the density on one side. And so I can tune the ratio U over J by the lattice intensity. And so this was done to actually, in the case of Bose-Hugbart model, to actually change a lot the ratio between, so starting from J much larger than U to U much larger than J. And so in the case where J is much larger than U, then atoms, bosons, they want to delocalize over the system, and you have a BEC, which has superfluid properties. So this is this situation here. On the other hand, when interactions are extremely large, putting more than one atom in a site or having fluctuation is energetically costly, and so you end up having one atom per site, and they do not move anymore. So this is an insulator state, which is referred to as Mott insulator. Great, and so this was first observed like more than 20 years ago now in this landmark paper, which from the Mini group. And so this is, let's say, a phase diagram that we measured on our experiment for this Bose-Hugbart Hamiltonian. So you have here vertically it's the temperature in unit of tunneling, and here this ratio U over J. And the only message here is that, well, we can tune this ratio U over J, so now we have a knob to change the interaction strength. And we can therefore go from weakly to strongly interacting system and see what happens in a controlled manner. Good, so we have a cold gas, we have a knob to tune interaction, and now we need a probe of microscopic correlations. So there are many different ways of doing so. One way is actually to do some fluorescence of absorption imaging, as Isabelle has mentioned. And if you look at the density, you can measure density-density correlations with this type of approaches. There were also ways which were very much inspired from solid-state physics to look at response function, such as neutron scattering or OPS. So in that case, you can shine some light and observe the diffraction. And in that case, you will also be able to probe indirectly density-density correlation. But this is mostly related and limited to density. But I said that I want to be able to go toward more than 2 objects, you remember, like at least 3, and to go non-Gaussian. So it's better to have single particle detection, and there were many new, let's say, tools to be developed to do so. So I'm just citing 2 of them. So-called quantum gas microscope, where the idea here is you look with an objective very close to atoms in an optical lattice, and you look at their fluorescence when they are in a lattice site. And if you do things well, you are able to take pictures like that, where each square here, it's a single atom in a single site. So you can detect atoms one by one in each of the lattice sites. This is for real space, position space, sorry. And you can do something a bit similar in momentum space. So as Isabelle mentioned, you can access the momentum space in a cold atom experiment by releasing the atoms from the trap. They expand. And if you wait a time which is long enough, the final position will be related to the initial velocity. And so you can actually detect atoms one by one, pretty much like that, by fluorescence. This is a picture from the Heidelberg group with fermions. So you have a fluorescence objective, and you see these are individual atoms here. Or another possibility is to use a specific atom, which is metastable helium, which is the one that we are using, and I will tell you a little bit about. And what you have here, it's a 3-dimensional picture where each tiny blue dot is a single atom. So we are able to measure in 3D single atom resolved distributions. So let me tell you just briefly how it works. If it wants, yes. So metastable helium-4 is a boson, and the specificity of this, one specificity of this atom is that we are producing BECs in this metastable state here, so far from the ground state. And especially this metastable state has a very large energy of 20 eV, which is kind of a huge energy at these temperatures. And what happens is that if we have the atoms, which are initially trapped here in these red arrows, they represent the standing waves that we put in 3 directions. And then at some time, t, I decide to switch off the lattice. The atoms will fall under gravity, and beneath them, I put a so-called microchannel plate, which is, let's say, a metallic plate. When the atom come close by to the surface of this metal, they can jump to their true ground state, releasing 20 eV of energy, and this is enough to extract 1 electron from the metal. And so then we amplify this electronic signal, and we are able to detect atoms one by one. And the good thing is that we are also able to tell where in the 2D plane of the detector they have fallen, and at which time. So we have 3 coordinates for each atom, and so therefore we can reconstruct the initial 3-dimensional velocity or momentum of these atoms. So this is not something that we have developed. This has been first developed actually at the Institut Optique by the team of Chris Westbrook and Denis Boiron now 20 years ago. Okay, so just to finish on that, well, let me skip the tomography. We can perform tomography of this single atom detector, and it works quite well, apart from, let's say, limited detection efficiency. But what I want to convey as a message here is that what we can do, we can select a small box in this momentum space, and then accumulate many shots and count how many atoms per shot I have in this small box. And I can then plot the probability of detecting a given number of atoms. And so here you have 2 examples. The square here, it's a Mott insulator. The blue here, it's a Bose superfluid. And you see that, therefore, we are able to perform full counting statistics. So to measure high order moments of certain quantities, especially the number of atoms we detect in certain region of the momentum space. And, well, I thought I should put this because there are people from, let's say, doing optics. So here you have a normalized correlation, so bosons, as a function of the order. So this is G2, G3, G4, 5, 6. And you have 2 different states. So one, let's say, a condensate, which depends how you want to describe it, but if you think about it as like a kind of coherent state, well, the normalized correlation function is equal to 1. And the Mott insulator, it's a thermal state, and you expect n factorial, and this dashed line is n factorial. So it works quite well. You see, like this is semi-log scale. Huh? It's orders of magnitude. Very good. So, do we, oops, are there questions? No? So, I don't know whether we'll have time to go through all this. The idea is, well, it will be short now that we have everything, now that the introduction is done. The idea is to remind about the type of quantum fluctuations present in a weakly interacting Bose gas, which is Bogoliubov theory. Then tell you about what we have done in the experiment about that. Then move to, as I said from the beginning, to stronger interactions, and where we expect to observe non-Gaussian correlations. And finally, if time permits, I would like to go to even larger interaction when the BEC is almost fully depleted, and we are looking at what happens across a condensation transition. Okay, so, well, this we have already said. If we take non-interacting Bose gas, let's say I put them in a trap, and I'm assuming 0 temperature, well, all the bosons will be accumulated in the lowest energy state, and this is the BEC state. And in terms of momenta, this state has an average momentum which is 0. And so what you will observe in terms of momenta, it's a distribution which is peaked around 0. If you would put some finite temperature, well, you will excite some particles above. And you will observe a broad pedestal here in terms of momentum. Okay, but this finite temperature is not what we are interested in. What we are interested in is the effect of interactions. So if I put this interaction term here, the one thing one really needs to just to realize is that this interaction term does not commute with a non-interacting Hamiltonian, which means that you have quantum fluctuations that will be induced by these interactions. And so this is the topic of this talk. So what will happen? Well, you will also deplete the BEC, excite some particles, but well, now I don't know how to represent it correctly, so just this background green means that they are all together somewhat. So it's not a single particle excitation. And in terms of momentum density, actually, it would be looking pretty much similar to what you would have with temperature, if you do not look into, let's say, specific quantitative detail. But the one thing which is completely different in the way you will remove atoms from the BEC. And the interaction actually should be written in terms of, I mean, can be written in terms of a 4-wave mixing process in momentum. And maybe we can keep that. So did I write it? So it's this contact interaction in position space. You do you Fourier transform that, and you end up with this term here. And this term is nothing but 2 modes, incoming K1 mode and K2 mode, that collide, and then give rise to 2 outcoming modes. And because of momentum conservation, the blackboard is really good. So I have AK1, AK2, and then I will have, let's say, K1 plus K3, and K1 minus, no, K2 minus K3. At least this I will keep it. And so I will discuss the interaction term along these lines. And so as I said, the first thing I want to do is, well, weak interaction, Bogoliubov theory. So maybe I can write this as well. So so Bogoliubov theory works if you start with almost a pure BEC. So what we will assume is that the number of atoms in the BEC N naught will be equal to the total number of atoms. If you do that, then it means that the we said that the mode of the BEC is the one with zero momentum. So you can approximate that with a classical field. So this is some, let's say, C number. And then we can put this into the interaction terms. So we have the four-wave mixing processes. And this, because it's almost equal to the, I mean, it's macroscopically occupied, gives you a hierarchy of terms. What is the largest term here that I can have? Well, if it's the term if I put all k's equal to 0, because in that case, if I put all k to 0, it means that the term is proportional to, so I have A naught 4 times, and this is proportional to A naught square. This is the largest term that you can have, and this is only mean field interaction. Okay, Gross-Witaevsky equation. So this is not Bogolyubov. Bogolyubov, you need to go to the second term, and the second term is the case where you will take two atoms which are in the modes of a BEC, and you will populate atoms outside the mode of the BEC, for instance, and the complex conjugate, of course. And because of momentum conservation, I will have Kn minus K. And there, Bogolyubov theory stops. So, well, this is essentially what is written here. And so therefore, this going to be second order term, and remember the hierarchy exists only because you have a macroscopic occupation of atoms in the BEC. This actually corresponds to linearizing quantum fluctuation, and because you linearize quantum fluctuation, what you have it's a quadratic Hamiltonian, so it's a Gaussian theory. And so the quantum depletion of Bogolyubov is that of having a pairing between modes at opposite momenta. The one thing I want to just to have you notice is that this is like kind of a cartoon picture that you should not take as a classical picture of two particles colliding and exiting the BEC, because you can take K, let's say, as large as you wish, but of course it will become less and less probable the larger is K, but still. And the final kinetic energy will be much, much larger than the BEC initial energy. So this will not conserve energy. And the reason is just because we are talking about quantum fluctuations, you cannot isolate one such scattering process. You really need to consider the system as a whole. So I think it's a nice illustration about the quantumness. Okay, great. So we have the prediction of Bogolyubov, and just to finish, the type of collective emerging property of Bogolyubov is, of course, the superfluidity. The initial paper was to describe superfluid properties of liquid helium, which happens not to be the good description because of a strong interaction in liquid helium, so you do not have the approximation used by Bogolyubov. But then it has been, let's say, confirmed with ultra-cold atoms. So we know that there is this macroscopic superfluidity. Well, can we observe this microscopic pairing between the modes in the depletion? And so this is what we have tried to do. Oops. I don't know why. I'm not moving the cable. Huh? Okay, so in terms of interaction strength, you remember we can tune the amplitude of the lattice to change the interaction strength, and here we are sitting here. So in the case where the system is the less interacting possible. So we measure momentum distribution in 3D. So this is the type of distribution we have. So each tiny blue dot, once again, it's a single atom. It's not noise on the picture. And you have here these huge blobs. What are they? It's just the BEC. This is the mode K equals 0, which is macroscopically populated. And then you have the copies here because you have a diffraction of the BEC, the coherent BEC on the periodic structure. So we are interested into the depletion of the BEC. And the question we want to ask ourselves is the following. It's really simple. If I detect one atom here, let's say at position K, well, what is the probability that I have an atom at opposite position minus K in the same experimental shot? And so this is what we do. We take many shots, and then we count the conditional probabilities. And this is what we obtain. So we are plotting, let's say, connected correlation. So it's only the average of the product of the densities minus the product of the averages to remove from let's say the correlation the signal which is statistically uncorrelated. And here you have this function which is plotted as a function of k plus k prime. And you see that there's a nice peak located at k primes equal minus k, which is exactly this type of pairing signature that one would expect. So we made a few tests, and let me just share with you this one. What we can do as well is to eat up the BEC. So you see in terms of density, so here it's the momentum density as a function of density. K equals 0, it's the BEC. We look in the green region, which is the depletion. And blue and red data, blue is cold and red is hot, right, as usual. It's not spins anymore. But we have increased by more than 1 order of magnitude the depletion. And this we did it by increasing interaction. So we did it by promoting atoms one by one outside the BEC, and certainly not through momentum correlated pairs. And if we perform the same measurements of this connected correlation at opposite momenta, no correlation signal. And
what does this green region mean? What do you mean that using?
So
how do you define the start of the green region?
Well, so that's a good question. This we just do it empirically. The one thing is we want to avoid having contribution for the BEC, okay? And the experiment is done in a finite system which has no periodic boundary condition. So a mode in momentum space is not well defined, and it's not something sharp. So you see this is semi-log scale, huh? But so this is the mode of the BEC. So let's say here the BEC will still contribute.
Just the inverse of the size of the system that defines it.
Proportional, yes. And so we just want to make sure to be outside that. Then actually there's another reason which is a bit more subtle, which is the fact that the excitation spectrum of Bogoliubov theory at low momenta are phonons. And if you, at finite temperature, you populate these phonons. And if you do a measurement, as we are doing after time of flight of correlation at opposite momenta, a phonon, being a superposition of two modes at k and minus k, would provide also a contribution to that. And if you, in our case, so the phononic part of the spectrum is at let's say, lower than 1 of the Ealing length. And in our case, the Ealing length is something like here. So we do not want to probe that in the sense that there we could not distinguish, let's say, contribution of phonons, or let's say not from a simple experiment, contribution of phonons from that of the quantum depletion. So being far from 1 over psi tells us that, well, it's safe to associate that to only 0 temperature.
So if you look at the correlation in the right zone, you will see the same blue signature on like some correlations.
No, well, I mean, you will. The problem here is that.
The center, but just on the phononic part of the thing, but not.
Yes, so if you would be able to populate and to probe only phonons, you would observe something like that. The issue is that here you have the BEC, and essentially, if we measure correlation here, what we see is the one of the mode of the BEC, which dominates everything. If I have time to the end, I will tell you interesting stuff about this. So just to contrast this with something which you may be familiar with, is that on the very same sets of data, we can also look at the type of correlation to find two atoms close by. So what is it? Well, this is nothing but, let's say, type of Embury, Brown, and Twist experiment, or bosonic bunching. And we did that. Actually, with Jacopo, a few years ago, we discussed the fact that both thermal and quantum depletion are expected to have a perfectly contrasted bunching. So here you have the measurement on the two sets of data I've already shown you. And what you see is that, well, yes, there is a bunching which is located at k primes equal k, which is two atoms coming close by. And this is like really different from what you have at opposite momenta. Blue and red are exactly the same set of data. It's just like instead of looking like this, we look like that. So we see that, of course, bosonic bunching, it's only statistics, it's independent of temperature, you always have it. While this pairing signal is very sensitive to temperature because it originates from quantum fluctuations. Okay, and just as I already said, so this is quantum statistic, but this is Bogoliubov theory, it's too much squeezing, and so all this is Gaussian. Nothing non-Gaussian here. Good. Well, I think I will skip that. Recently, we've wondered with colleagues at Institut d'Optique, like Victor Gondré, Denis Boiron, whether there is an entanglement in the pairs we detect. Now we think we have some clue about that, but let me rather go to increasing interactions. So, yes. So this is what is written on the blackboard. The first terms, but now we can, still assuming that the BEC is macroscopically occupied, we can add the other terms of the four-wave mixing process. So a term where you will have only one atom, there should not be a at here, only one atom in the field of the BEC, and then a term when you have no atoms in the field of the BEC. So these terms, they correspond to non-linearized quantum fluctuations, and you see that they are multimodes, because you have, like, let's say 1, 2, 3 different K modes, or even 4 different K modes. So for sure, they will induce correlation between more than 2, and you will have some non-Gaussian correlations. But when we look at them like that, it's not so easy to get an intuition about what they are. And actually, we realize that there's something very, very simple. If you look at this term, so the third term, so you have one atom at finite K that collides with an atom in the BEC. Well, actually, if you say, well, this guy has been, as an origin, a first scattering event of two atoms in the BEC, then what you are left here is 3 atoms in the depletion with a total sum equal to 0. You will tell me it's obvious because you have 2 times momentum conservation, so of course you keep the total momentum. But the nice thing is, this directly shows you that what you have is a triplet, which is momentum correlated. So at Bogoliubov, you have a pair with total sum equal to 0, and if you add another term, you get a triplet. And if you add the fourth term, you get a quadruplet. So it's just like the hierarchy of terms in the interaction gives you a hierarchy of momentum correlated n-uplets to a larger and larger order. Okay, so we will be moving a bit in terms of interaction and go in this, let's say, more interacting region here. This is done in collaboration with Tommaso Roschilde from Lyon. And now what I will be plotting, so this is this connected two-body correlation at opposite momenta. What I will be plotting now is we will repeat this experiment with different value of the amplitude of the lattice, and we will count typically the integral, like the total number of pairs. And we will plot this signal as a function of interaction. And this is what we observe. This amplitude of connected two-body correlation as a function of increasing interaction. So as we increase the interaction, the depletion of the BEC is also increasing. So the first part is rather simple to understand. This is what predicts Bogoliubov theory, because all the depletion is made of pairs at opposite momenta. And therefore, if you increase the depletion, well, you will increase the number of pairs. And so this is what we observe. But Bogoliubov tells you that as long as you increase the depletion, you will always increase the number of pairs, which is clearly not what we observe. And so this non-monotic behavior is clearly beyond Bogoliubov. And one possible origin of this, if we come back to the fact that we would have triplets, which are momentum correlated, is that to create a triplet, you need to destroy a pair. And so when you start to have larger n-uplets kicking in, then the pair number will stop increasing, or at least it will not increase as much as it would have in the Bogoliubov picture. So to have a numerical, let's say, support for this observation, Tommaso performed simulation of 3D quantum rotors, which is a system which is much simpler than the Bose-Hugbart Hamiltonian. It's difficult to compute a correlation for the Bose-Hugbart Hamiltonian beyond, well, actually, at the moment, people are only doing density in momentum space. So the good thing about this model of quantum rotors is that Tommaso does is that it includes quantum fluctuation at all orders, so beyond linearized, and is plotting the same quantity as a function of, let's say, u over j with some normalized filling factor. And you see that at small temperatures, it also has an increase and then a decrease, similarly to what we have in the experiment, which of course vanishes when you increase interaction. So this is qualitatively similar. And so therefore, this onset of this maximum pairing here can be considered as the onset of a strongly correlated system. I told you about triplets. So Tommaso tried to see whether he can look for triplets in his simulation. So I'm sorry, I don't know why it stops. And indeed observes triplets. So what is plotted here, it's the connected free body correlation. So it's the analog of two body. You have a total number of correlation and you subtract contributions to all lower orders. So a pair with one atom or three different atoms. And you also observe an increase of the free body and so the number of triplets as a function of interaction. And as well as the two body, the triplet at some point also start decreasing. We asked whether he could go for quadruplets, but he said that it was not possible. Already this took him like very long time. But of course, I mean, he said, but look in your experiment. And we've been fighting a lot in the experiment, and we may, but there's a big possibly, have a first hint of this triplet. So this is from last Friday. Well, actually, the experiment is from, let's say, 10 days ago, but the computation now takes us like almost a week. So this is something like 20,000 shots of the experiment with 5,000 atoms in each, and you need to compute these free body connected correlation, and so for the moment it takes very long. What you see here, it's the free body correlation as a function of, let's say, typically the volume over which we integrate. So this is kind of a normalized G3, and there is this small hint here, but okay. We are very excited, but I'm not sure it is yet the case. Okay, so do I have a few minutes? 2. So we all know everything about quantum phase transition, continuous quantum phase transition, and so I can jump to the very end. So what I wanted to tell you is what happened when we go here. So here we cross the transition, which is a BEC transition or a MOD transition at finite temperature. And this is something we are doing in collaboration with Nicolas, Adam, and Tommaso as well. So I will just flash, sorry for that, but then I mean, I'm here to discuss, so I will be very happy. So we know a bit about continuous phase transition, let's say like a ferromagnet to paramagnet, superconductor to fermi liquid, and so on. And for this type of continuous phase transition, you have an order parameter which is non-zero, let's say, in the ordered phase here, and in average 0 in the disordered phase. You have some substitutabilities that diverge. And what we call the critical regime, it's the regime where physical quantities follow scaling laws, algebraic scaling laws with the critical exponents. One point which is actually less known, at least to me it was not known, is the following. It's that this universal scaling actually is very broad and it has a substructure. So what is plotted here, it's the correlation length of the order parameter. This is the control knob, like where you have the transition. 0 is the critical transition. And you know the correlation length diverges at the transition. So when this correlation length is larger than a typical size, which is often called Ginzburg size, which is the typical length scale over which you have the microscopic details of your model that are playing a role. If the correlation length exceeds that, then you can forget about what happens at the very microscopic level, and you enter this universal scaling where only symmetries are giving you the physics. And this is the reason why you have these universality classes and universal exponents and so on. But actually, since this correlation length diverges, it can also at some point exceed the system size. And there, in this regime, because your correlation length is over the entire system, you have no longer something like a central limit theorem, and so what you expect, especially for the order parameter, is a statistics which is non-Gaussian. And so this is actually something that you already have somehow in the mean field. Well, if you interpret Landau free energy, in the ordered phase, you have like a finite value of the order parameter. So this is the free energy. The system is there and fluctuates. And locally, you can be describing the fluctuation as a parabola. So it's Gaussian. This is the same in the disordered phase. And at the critical point, the Landau's potential are flat. So you have large fluctuation. And locally, you cannot approximate them by a parabola. So this is non-Gaussian. So actually, this is something which is not so easy to see. If you take macroscopic systems, like solid-state systems, with n equal 10 to the 23 particles, L is very big, so which means that this green region is extremely narrow. So it typically goes in the thermodynamical limit. It's only the transition point where you have these non-Gaussian statistics. So it's difficult to observe. And on top of that, if you want to show non-Gaussianity, you need to be able to probe moments larger than 2. So you need to be able to do full counting statistics. So we are in a finite size. So this green region can be much larger. And we are able to perform the full counting statistics. And we do that for the condensate BEC, which we count the number of a BEC, which is, let's say, modulus square of the amplitude of this order parameter. We can do that across the phase transition. So these are typical counting statistics of, let's say, psi, which is the square root of n Beck. So we count how many times we get square root n Beck as a function of square root n Beck. And from that, you can use statistics to infer the Landau's free energy or effective free energy, taking the log of this probability distribution. And you see that what we recover is that we have like this type of Landau potential in the ordered phase when we have a BEC, and then we cross the transition, it becomes flat, and then in the disordered phase, it becomes well approximated by Gaussian around 0. And the very last point, which is the question mark, is that we've been measuring cumulants to show that it is non-Gaussian. So this is the cumulant, these are the cumulants of the order parameter, average, second, third, 4, 5, 6. And the very funny thing is that if you look at high order cumulants, you see that they are 0 in the disordered phase, 0 in the ordered phase, and they are non-zero only in a narrow region, so the one which is non-Gaussian. And on top of that, they oscillate. And in numerics, we have first hints that you have also oscillations, and not only, we can also rescale if you do the proper finite size scaling analysis, and these oscillations of the cumulants are critical. And so, well, this is an open question. Where do this critical oscillation of the high order cumulants of an order parameter are coming from? This we are still trying to understand. Okay, I stop here. I've been trying to bring you to a journey between, let's say, non-interacting to a strongly interacting system, talking about Bogoliubov and the pairing that we have in the depletion. Then you go beyond Bogoliubov, you obtain momentum correlated pairs, triplets, quadruplets, which are non-Gaussian, even though the BEC is still macroscopic. And if you keep increasing interaction, and now like have a BEC which is non-macroscopic, then you observe nice non-Gaussian features. And with that, let me thank all the guys and persons who actually done the job. So Thomas Chalopin is a permanent researcher working in the team with us, and many of his works have been done by Paul, Giraud, Yann Philippe, and Maxime. And with that, thank you in course.